Yeah, so I've been dabbling in functional programming since a young age, and yeah, that's my dad's fault. He's now a happily retired closure dork. And I've also been in the blockchain space for a bit over a decade now. So it's funny, I've had my hands in both of these spaces for like 10 years, but I only just realized what they have in common. Yeah, so the sad thing is that blockchain implementations are plagued by the worst kind of state, global mutable state. And they're not really dealing with that state in a very disciplined way. So our plan for today is to investigate this through a functional programming lens and see if we can try to tame that dragon. And we're going to be looking at Bitcoin specifically, but the same principles apply to most blockchains. So first off, what kind of state are we talking about here? Because there are lots of different pieces of state in a program. But what we're going to talk about today is what I call consensus state. And that's specifically the state that you need in order to enforce various consensus rules. Rules like, a block needs to have a certain amount of proof of work, or a transaction can't spend any Bitcoins that were spent in a previous transaction. So we use this state to validate a block, and then we apply the block to the state such that we can validate the next block. The other reason I call this consensus state is because this is actually the state that the Bitcoin network is reaching consensus on. We need everyone to agree on what the state is so that everyone can agree on whether a given block is valid or not. So we'd really like both of these functions to be pure because pure functions are deterministic, and that seems like a nice property to have if you're trying to do distributed consensus, right? But unfortunately, in Bitcoin today, these functions are not pure. Actually, these functions don't exist in the Bitcoin codebase today because actually the Bitcoin codebase doesn't even define this consensus state type. Instead, the state lives in multiple places. Some of it is mutable, some of it is immutable, some of it is resident in memory, some of it is in a database on disk, and there's nothing really tying it all together. I'm like, isn't that kind of crazy? I mean, this is, as I said, this is literally what we're reaching consensus on, the state of the Bitcoin network, and yet the system itself does not seem to have a clear conception of what it is. So this is the refactor that we're undertaking here. First, we have to figure out what this state is, and then we need to figure out how to implement these pure functions. So you might think like there's no great mystery here. This consensus state that I'm talking about is just the blockchain, right? Because that's what we're reaching consensus on. Sort of. If we just take that at face value and use that as our consensus state, we actually run into a lot of problems. For example, there are a lot of consensus rules that only come into effect as of a certain block height, so like the length of this blockchain. But the blocks themselves don't contain their height. So if you want to implement that kind of logic, you'd have to literally initialize a counter to 0 and then iterate over the whole chain, incrementing it by 1 in order to calculate the block height. Obviously, that would be insane. So no one does that. What you do instead is you extend your state type to contain the height. So this is a very simple working definition of our consensus state type. So then when you apply a block, you can just increment the height. You don't need to recalculate it from scratch every time. And this points to something interesting, which is that we can choose to represent this consensus state in different ways. Like just the blockchain is a valid representation. It's just a very inefficient one. But we can also augment it to trade storage for compute in various ways. So it's okay to use a different representation as long as we preserve the semantics of all the consensus rules. So while it's true that the network is reaching consensus on some state, we can't say that it's reaching consensus on any particular data structure or sequence of bytes. Like the true consensus state is really more like an entropic limit that each implementation chooses to approximate in a different way. But that's getting a little philosophical. The point is that we have a choice in how we implement the various consensus rules. And crucially, none of the rules actually require us to store the entire blockchain, which is good because the blockchain is like 600 gigabytes of data. There is certain information that we need that we can only get by processing the whole blockchain, but we don't need to keep that around once we're done processing it. And what this means is that we can represent our consensus state as an accumulator. And what I mean by accumulate here is basically something that you use with fold, aka reduce. It's a value plus a function that updates that value. And that makes sense because our apply block function here, like it has exactly that kind of signature, right? It takes a state and a block, and it returns a new state. So yeah, it turns out Bitcoin is actually just computing a very, very slow fold on a lot of data. So let's take a look at one of Bitcoin's consensus rules, and we'll see how Bitcoin implements that rule today, and then we'll see how to do it with a more efficient accumulator. So this is the code for Bitcoin's median timestamp rule, which says that a block's timestamp has to be greater than the median of the previous 11 blocks timestamps. And so you can see in this code, this function is taking a pointer to the tip of the blockchain, and then it follows the parent pointers back 11 times, extracts the timestamp from each block, and then sorts them, finds the median. And like, yeah, this works fine, but to me, it really illustrates what's wrong with Bitcoin's approach. This function operates on 11 timestamps. It's like 44 bytes of data. But the function signature doesn't indicate that at all. We're just passing in the entire blockchain, and we let the function kind of pick and choose whatever it needs from that state. So this is like the moral equivalent of giving a user space program ring 0 access. So we want to replace this with something a bit more narrowly focused. So what do? Do we just add this median timestamp to our state like that? That would work to validate one block, right? You just compare the timestamp to this median in the state. But there's no way to take that median and combine it with a new timestamp to get a new median. So we can't actually apply. What we need is an accumulator that can represent this sliding window of 11 timestamps. And so we can use something like a DQ for that. So when the new block comes in, you apply it by pushing its timestamp onto the front and then evicting the oldest entry. So now we have an accumulator that implements that same consensus rule, but without needing to operate on the entire blockchain. And so if we can repeat this process for all the other consensus rules, then we can eliminate that blockchain field from our state. And then we'll have a nice compact accumulator that explicitly represents the consensus state, which we can then transform with pure functions. Unfortunately, when we try to do this, we run into a bit of a snag. And the snag is UTXOs, unspent transaction outputs. So an output is like a tranche of some Bitcoins. Every transaction spends some outputs, and it creates some outputs that flow to new transactions. So if I send some Bitcoins to you, I'm spending an output that belongs to me, and I'm creating an output that belongs to you. And so when you're validating a transaction, it's really important to check that all of the outputs being spent are actually spendable, meaning they were created in a previous transaction, but they haven't been spent yet. In fact, you could argue that this is the single most important consensus rule in Bitcoin because it prevents double spends and just creating money out of nowhere. So it's not difficult to design an accumulator for this rule. It's just a set, right? When you apply a block, you delete the outputs that were spent, and you insert the outputs that were created, and then you can validate a block just by checking to see if the outputs are all present in that set. The problem with this is that the set is going to be really, really big. Not as big as the whole blockchain, but still, it's got millions of elements in it. So like we're talking multiple gigabytes of data, which means you're not going to be using an in-memory map for this field. We have to use a different type. Yeah, this is using some non-traditional reference syntax where the asterisk go in the middle. Yeah, so this sucks. I mean, it's not the end of the world. At least we have an explicit state type now. And that's an improvement over the status quo, but it's a shame. We had this nice, tidy set of immutable values, and now we have to bolt an entire database onto it, which means we have to contaminate our nice, pure functions with I/O. And you can do I/O in Haskell. There's ways of interacting with the database, but it's mostly cope, right? It's like you are mutating a big singleton on disk. Also, databases are like really complicated piece of software. Like Bitcoin is using LevelDB for this, and that's tens of thousands of lines of code written by people with no connection to the Bitcoin project. And so you really don't want to drag a dependency like that into your consensus code. So we really want to avoid this. But how do we do that? Like, we tried using an accumulator here, but even the accumulator was still too big. Well, fortunately, that's not the only possible accumulator that implements this consensus rule. In 2019, I guess this is 5 years ago now, a Bitcoin developer, Taj Dry, showed that you can use a cryptographic accumulator based on Merkle trees to implement this rule. So a Merkle tree lets you prove that a particular leaf is present in a tree, and the verifier only needs to know the root hash of the tree. So the idea here is that we put all of the transaction outputs into a big Merkle tree, and then the transaction can prove that its outputs are in the tree. And that way you can enforce the same consensus rule just by verifying Merkle proofs instead of having to do lookups in a giant database. So this actually, sorry, question?
That solves the problem of this being so huge?
Yeah, so what solves it is that we only need to store these root hashes instead of every element. So this is actually the true data structure. It's not a single tree. It's actually a set of perfect binary trees. And you store the root of each of these trees. So in total, it's about 1 kilobyte of data. And this allows you to do a sort of arithmetic. So you can take the roots of 2 equal-sized trees, and you hash them together, and you get a new root that's like 1 level up. And so when you add an element, in our case, a transaction output, into this accumulator, what you're actually doing is adding it as a tree of size 1. And so if there's already a tree of size 1 present in the set, then you hash them together, you get a tree of size 2, and then you carry that tree up until you hit a gap. So it's actually exactly like binary addition, where you just keep carrying 1s until you hit a 0. And so this is what makes it an accumulator. If we just had one big tree and we were just storing the root of that one tree, then we wouldn't be able to add new elements in this way. So Taj calls this a Merkle forest, but it turns out this data structure is so useful and great that people just keep independently rediscovering it. So it's also been called the Merkle mountain range. I actually also independently rediscovered this. I called it a binary numeral tree. And just earlier this week, I learned that this same data structure shows up in the Okazaki functional data structures paper, where it's called a binary random access list. His version is a Merkle tree, though. It's just a regular tree. So yeah, I don't have time to fully nerd out on this, but I did write a paper on this tree, which you can find on ePrint and also on my personal website. So before we move on, I want to point out that this accumulator is different from the other accumulators. In order to make this accumulator work, we had to change the input and not just the state. So the blocks now need to contain these Merkle proofs, right? And those Merkle proofs actually need to change. They need to be updated every time the state changes. So it's really more of a collaborative effort here. So the inputs are getting a little bigger, but this allows the state to become much, much smaller. And this kind of suggests that there's actually a spectrum here where you can have really big states and really small inputs, or vice versa, or anywhere in between. Of course, there are some downsides to shrinking your state. You lose local information. Like with this Merkle accumulator, we're not storing all the outputs locally anymore, and so we lose the ability to run certain queries. Like, you can't find out which address controls the most bitcoins. But I don't know, I think that's a small price to pay for shrinking our state down from multiple gigabytes down to 1 kilobyte. If you take this to the extreme, you could actually move the entire state into the input and then have no local state at all. And that could work. You'd have like a totally stateless Bitcoin node that you just throw blocks and states at, and it verifies them. But like, I don't know, it seems kind of cursed to me. It's like you can't do anything. Like you don't even know what the current block height is or like the timestamp of the most recent block. You're just totally state free. So I guess my heuristic around this is that you want to make your states small enough to be wieldy, but no smaller than that. And 1 kilobyte is perfectly wieldy. So with this fancy cryptographic accumulator, we now have our complete state type. We have a nice compact accumulator that contains all of the information necessary to validate a block, and it fits in like a network packet. And as it turns out, there are a lot of cool downstream effects of this, both for the programmer and the end user. First off, these consensus functions, they can be pure. And I don't need to preach to the choir here about why pure functions are great, but I will anyway. You get determinism, which is great for consensus, as mentioned. You get easier testing. The data involved here is all immutable, so you don't need to protect it with a mutex. And the code is faster because you're not doing any I/O, right? Because we can throw out this database, so that's nice. That makes it much more tractable to do things like a security audit of every line of code in your consensus module, or even like formal verification. But there's an even bigger conceptual shift that happens when your states are this small, which is that you can permanently store the state for every block. And so, effectively where we used to have a chain of blocks, now we can have a chain of states. And it's like, well, where did the blocks go? Well, the blocks are now actually the edges in this state diagram. And I don't know, to me, I just find this a lot more intuitive. Like a blockchain is like a sequence of diffs that are being applied to some state, and the state is just sort of implicit. Whereas this is much more just like a state diagram. You have blocks that are transitioning you between them. It's like, okay, we've all reached consensus on this state, and then we all apply this particular block, and so we have now all transitioned to this new state. So there's a practical consequence of this. So say that we're running a Bitcoin node, and we're at state A, and we receive this reddish block down here that attaches to a chain that is not our main chain. But if this block is valid, then we're going to need to reorg because that will make that the new best chain. The problem is that in order to validate the block, we have to be at state B. And so if you're in the traditional model of Bitcoin today where you only have this one big singleton state, it's like, well, how do you get from state A to state B? You need to undo the effects of all these blocks until you reach the common ancestor, and then you need to apply the effects of all the blocks going down this other chain until you get to B. And then you can finally validate the block. And maybe you do all that, and you discover that this block is actually invalid. This peer just like wasted your time. So you ban them, of course, but then you need to undo all the work that you did. And this whole time, you have to be holding a mutex to protect any other part of your system from observing the intermediate state. So it's a very unfortunate situation. But if states are cheap and you can just store the state for every block, then when this block comes in, it's like, you just fetch the state B. It's like you don't even have to lock anything. And this is possible because you're not limited to being in one state at a time. So even this meme is kind of misleading because we're not going from A to B. A and B, like we just have both of them at the same time. Different pieces of code can be operating on different states. Another consequence of this is much faster syncing. So if you want to join the Bitcoin network today, what that entails is you're starting at the genesis state, and then you are applying all 850,000 blocks to that state so that you can arrive at the same final state as everyone else in the network. And that takes a really long time. Actually, it takes so long that when you do this today, you aren't actually validating all the blocks. They put checkpoints in that are hard-coded that say, like, before this block height, just assume that the block is valid because you don't want to waste time validating signatures for blocks from like years ago. Now, you could, in theory, just import the state, the final state that you would arrive at from someone else. But it's not really feasible because that state is too big. It's multiple gigabytes. And like, who is going to serve that data to just like a random peer? But again, small states make this possible. You could download from a peer, fits in one packet. I mean, heck, you could fit it across like a couple of QR codes that are just like on a pole somewhere in a public space. You could base 64 encode it and put it in a config file. Lots of options here. So as they say, quantity has a quality all of its own. So main takeaway here is know your enemy. We know that this consensus state is critical to Bitcoin as a system, and yet the implementation of Bitcoin today does not even define it. And without knowing what your state is, it's hard for you to interact with it in a disciplined way. There's like this latent fear and uncertainty around like touching it the wrong way and breaking it, particularly for a new contributor to the code base. But once we brought the state out into the light and made it more legible, we were able to get a better handle on it. And in the end, with the help of our fancy Merkle accumulator, we shrank it down to just a tiny little slab of immutable data. So we didn't have to destroy the state. Actually, the state plays an even more important role in the system than before. What we did was we transmuted the state into something small and cheap and ubiquitous. We took Cthulhu here and we turned him into a Funko Pop, basically. we turned him into a commodity. And that not only allowed us to interact with our state in a more disciplined, functional way, it also unlocked new functionality, performance optimizations, and it gave us a new perspective on blockchains as a whole. So that's all I got for you guys. If you want to come and talk to me later, happy to chat. Don't really want to take questions up here. But yeah, thank you, and enjoy the rest of the conference.